Welcome back to Understanding Quantum Information and Computation. My name is John Watrous, and I'm the Technical Director for Education at IBM Quantum. This is the 11th lesson of the series, and it's the third lesson in the third unit, which is on the general formulation of quantum information. This lesson is about measurements, which represent an interface between quantum and classical information. When a measurement is performed on a system while it's in a quantum state, classical information is extracted, revealing something about that quantum state, and generally changing or destroying that state in the process. In the simplified formulation of quantum information, which was discussed in the first unit of the series, we typically restrict our attention to projective measurements, including the simplest type of measurement, standard basis measurements. It is, however, possible to generalize the notion of a measurement, and that turns out to be a pretty useful thing to do. In this lesson, we'll talk about measurements in full generality, including how they're described in mathematical terms and how they fit into the general formulation of quantum information. Toward the end of the lesson, we'll also take a look at a couple of fundamental notions connected with measurements, namely quantum state discrimination and quantum state tomography. So let's get started. Here is an overview of the lesson. As we often do, we'll start with the basics, including a couple of different but equivalent ways that we can describe measurements in mathematical terms. In particular, we can describe measurements by collections of matrices, and we can also describe them as channels, which I alluded to in the previous lesson. We'll also discuss partial measurements, or in other words, measurements that are performed on just one part of a larger compound system. Then we'll move on to Naimark's theorem, which is a fundamental fact concerning measurements that basically says that general measurements can always be implemented in a simple way that's reminiscent of Stein spring representations of channels. In short, general measurements can always be implemented by first introducing an initialized workspace system, then performing a unitary operation, and finally performing a standard basis measurement on the workspace system. This turns out to be pretty easy to prove, and we'll see how that goes. And we'll also see how this connects to so-called non-destructive measurements, which I'll describe. Finally, in the last part of the lesson, we'll discuss quantum state discrimination and quantum state tomography. We'll begin with mathematical descriptions of measurements. Measurements provide us with an interface between quantum and classical information. When a measurement is performed on a system while it's in some quantum state, classical information about that quantum state is extracted. In addition, the quantum state is generally changed or possibly destroyed completely. Initially, we'll focus our attention on so-called destructive measurements, where a quantum state goes in and just classical information comes out. So there's no specification of the post-measurement quantum state of the system that was measured. Intuitively speaking, we can imagine that a destructive measurement destroys whatever system was measured. So its state after the measurement takes place isn't specified. This doesn't literally mean that physical devices are necessarily destroyed. It's just a mathematical description, and it's a very useful one because it helps to keep things simple and to focus in on the essential mathematical aspects of measurements. There are, in particular, two equivalent ways to describe destructive measurements, which I mentioned during the overview of the lesson. One way to describe a destructive measurement is by a collection of matrices, where, in particular, we have one matrix for each possible measurement outcome. A second way to describe a destructive measurement is by a channel, where the input is the state of whatever system is being measured, and the output is always a diagonal density matrix, which we can interpret as a description of a probability distribution over the possible classical measurement outcomes. The two descriptions are equivalent, and that's pretty useful because it allows us to pick whichever description is more convenient in a given situation. We'll also talk about non-destructive measurements, where in addition to a classical measurement outcome, the post-measurement quantum state of the system that was measured is also specified. Non-destructive measurements are important and they arise frequently, but there is a sense in which they're somehow not as fundamental as destructive measurements in mathematical terms. In particular, as it turns out, non-destructive measurements can always be described as compositions of channels and destructive measurements and we'll see how that works a bit later in the lesson. Now let's take a look at how measurements, meaning destructive measurements, can be described as collections of matrices. Throughout this discussion, we'll suppose that X is a system that's being measured, and just for the sake of simplicity, we'll make a couple of assumptions. First, we'll assume that the classical state set of X consists of the integers from 0 to n-1 for some positive integer n, and the possible outcomes of the measurement are the integers from 0 to m-1, again for some positive integer m. There doesn't need to be any relationship between the numbers n and m. They're both arbitrary positive integers. And of course, we could replace these sets by arbitrary classical state sets if we wanted to do that. First, let's recall how projective measurements work, which we first talked about back in the third lesson of the series. Given that we're assuming that the measurement outcomes are the integers from 0 to m-1, we describe a projective measurement by a collection of projections, pi0 through pi m-1, that's summed to the identity matrix, and these matrices all have rows and columns corresponding to the classical states of X, or in other words, these are all n by n matrices. If X is in a quantum state that's described by a quantum state vector psi, then each possible measurement outcome, A, appears with probability equal to the Euclidean norm squared of pi A multiplied to the vector psi. The Euclidean norm squared of any vector is equal to the inner product of that vector with itself, so we get the expression that's shown on the screen. And we can simplify that just a little bit by using the fact that pi A is a projection, so multiplying it to itself doesn't do anything. And finally, we can rewrite the expression we've obtained in a slightly different way using the cyclic property of the trace, again, as is shown on the screen. And if it's not clear why we want to write the expression like this, the short answer is that we'd like to understand how projective measurements work for density matrices. And in particular, by linearity, we have that if the state of X is described by a density matrix rho, rather than a quantum state vector psi, then the probability for the outcome A to appear is given by the trace of the projection pi A times the density matrix rho. That has to be the case because, as we've seen, we can always think about a density matrix as being a weighted average of pure states. And if we average the corresponding probabilities, we get this expression because the trace is a linear function. So that's the expression we're going for. And we can clean things up just a little bit to focus in on density matrices. The main point of doing this, by the way, is to establish a point of reference to what we've already learned, and to see that this description of projective measurements is, in fact, a special case of a more general description of measurements that we're about to see. So what I'll do now is to replace this description of how projective measurements work for density matrices with the description for general measurements so we can understand the relationship. And here it is. A general measurement, not necessarily a projective measurement, is described by a collection of positive semi-definite matrices, p0 through pm-1, that's summed to the identity. And if this measurement is performed on X while it's in a state described by a density matrix rho, then each outcome A appears with probability equal to the trace of PA times rho. In short, the only thing that's changed is that we've relaxed the condition on these matrices. In particular, the matrices don't need to be projection matrices, they just need to be positive semi-definite. And correspondingly, I've replaced the letter pi with the letter p, because pi is a conventional name for a projection, whereas I like to use the letter p for positive semi-definite matrices. This is a generalization of the description we had for projective measurements, by the way, because projection matrices are always positive semi-definite, and in fact they can alternatively be defined as positive semi-definite matrices whose eigenvalues can only be 0 and 1. We can observe that this definition makes sense in that we always obtain a probability vector for the outcome probabilities in the following way. First, these numbers that I've referred to as outcome probabilities are always non-negative real numbers. And that's because both PA and rho are positive semi-definite, and the trace of the product of two positive semi-definite matrices is always a non-negative real number. And I'll leave that for you to think about why that is. And second, the numbers have to sum to 1, because the trace is linear, the matrices P0 through Pm-1 are required to sum to the identity, and density matrices have trace equal to 1. So, regardless of what density matrix row we started with, the outcome probabilities will indeed always form a probability vector. Now let's take a look at a few examples. I already mentioned that projective measurements are a special case of general measurements because projections are always positive semi-definite. But it's nice to start simple, so let's begin with a standard basis measurement of a qubit. We can represent a standard basis measurement of a qubit by two matrices, P0 and P1, defined as is shown on the screen. P0 is ket0 bra 0, and P1 is ket1 bra 1. These are both positive semi-definite matrices, and indeed they're projections, and they clearly sum to the identity, so together they describe a measurement. If we apply this measurement to a qubit in a state described by a density matrix row, then the probability for the outcome 0 to appear is the trace of P0 times rho, and the probability for the outcome 1 is the trace of P1 times rho. And by the cyclic property of the trace, we obtain the two diagonal entries of rho as we expect. Here's another example where this time the matrices aren't projections. They are positive semi-definite though, and they do happen to be density matrices, but that's not important. But what is important is that they sum to the identity. So together they describe a measurement. We can see what happens when this measurement is performed on a qubit in the plus state, for instance, just to see how it works for one example of a state. And a calculation of the probabilities is shown on the screen. Notice in particular that although the plus state is a pure state, and we can represent that state by the quantum state vector ket plus, we do have to plug the density matrix representation of that state, which is ket plus bra plus, into the formulas to get the probabilities. And let me also remark that because we're talking about a destructive measurement, there isn't any specification of the post-measurement quantum state of this qubit. So all we have is a specification of the outcome probabilities. Here's a final example for now, and it's a pretty interesting one. Once again, it's a measurement of a single qubit. And to describe it, we'll start by defining four quantum state vectors known as the tetrahedral states. And the reason that they're called the tetrahedral states is because they correspond to the four vertices of a regular tetrahedron inscribed within the Bloch sphere. And to be clear, when we say that this is a regular tetrahedron, we mean a four-sided solid where each of the faces is an equilateral triangle. So there's a perfect symmetry here. Every edge has the same length, and it's the same angle that's formed between any two adjacent edges. And now we can define an interesting measurement with four possible outcomes as is shown on the screen. Or, in words, we can take our matrices to be the density matrix representations of these states divided by 2. Now, these are definitely positive semi-definite matrices because they're density matrices divided by 2, and you could go through the arithmetic to check that they do in fact sum to the identity, but another way to see that is to think about the symmetry. If we average these four states together, we get the completely mixed state, which is at the center of the Bloch sphere. But because we're dividing each one by 2 rather than 4, we get twice the completely mixed state, which is the identity. I won't say anything more about this measurement for now, except to observe that it isn't a projective measurement, but it is a nice example, and we'll see it come up again later in the lesson. Another way to describe general measurements is as channels, as we'll now discuss. The idea here is that classical probabilistic states can be represented by diagonal density matrices, and so, because measurement outcomes are classical, we can think about measurements as being channels where the output is always a diagonal density matrix that describes the measurement outcome. So let's take a look at this in a little bit more detail. If we think abstractly about a general measurement, we can describe that measurement as a channel phi. The input system for the channel is whatever system X is being measured, and the output system is a system Y whose classical states correspond to the measurement outcomes, which we're taking to be the integers from 0 to m-1 for some positive integer m. And because measurement outcomes are classical, we require that for every input density matrix row for the system X, the output phi of rho must be a diagonal density matrix. For example, if we think about a standard basis measurement of a qubit, and we think about that measurement as being described by a channel, we can express it as we have here on the screen. If the input density matrix is rho, then we'll get the outcome 0 with probability equal to bra 0, rho, ket 0, and we'll get the outcome 1 with probability bra 1, rho, ket 1. And so, if we express these classical measurement outcomes as density matrices, we'll get this expression for the corresponding channel, and it turns out that it's none other than the completely dephasing channel. And that's consistent with the idea that the completely dephasing channel represents an extreme form of decoherence, which can mean different things, but when I use that term, I'm talking about the tendency for quantum states to become classical because the environment around whatever system we're talking about is watching in some sense, or in other words, it's measuring. So, measurement outcomes can be described as channels, as I've just described, but this is not just a possibility, it's a characterization of general measurements, and what I mean by that is the following. Of course, there are channels that don't represent measurements because the output might not always be a diagonal density matrix. But if it is the case that the output of a channel is always a diagonal density matrix, regardless of what input state rho we choose, then it is necessarily possible to express that channel in the form that's shown on the screen for some choice of a measurement, meaning a collection of positive semi-definite matrices that sum to the identity. And that's nice for multiple reasons, including the fact that it basically tells us that our definition of measurements as collections of matrices isn't missing anything. Another way of saying that is that this way of thinking about measurements as channels is operational, or axiomatic perhaps, in the sense that it captures what a measurement should be, which is a physical process that transforms quantum information into classical information. And it turns out that it's completely equivalent to our first description of measurements, which is purely algebraic. I won't go through the proof of the equivalence in this video, but it isn't difficult, and if you're interested, you can find the proof in the written material for the lesson, which is linked in the video description. We've discussed what happens when a general measurement is performed on a system in a given state, at least for the case of destructive measurements. Next, we'll talk about partial measurements, meaning that just one part of a compound system is measured. To be precise, let's suppose that we have a pair of systems, xz, that together are in a state described by a density matrix rho, and a measurement described by a collection of positive semi-definite matrices that sum to the identity is performed on the system X alone. Naturally, this results in a measurement outcome, and because we're talking about destructive measurements, we can imagine that the process of measurement destroys the system X. But we still have the system Z to worry about, and we need to understand how the measurement of X affects the state of Z. First, let's talk about the outcome probabilities. Because we're talking about a measurement of the system X alone, the probabilities for different outcomes to appear can only depend on the state of X in isolation, which is to say that they can only depend on the reduced state of X. In particular, the probability for a given outcome A to appear is given by the same formula from before, which is the trace of PA times the reduced state of X, which we denote by rho sub X. The state rho sub X is obtained from rho by tracing out Z, so we can make that substitution. And although it might not be immediately obvious, the expression we get can alternatively be written as is shown on the screen. It's the trace of PA tensored with the identity matrix on the system Z times rho. Now that's an equality that's definitely worth taking some time to verify. It's intuitive. We're not doing anything at all to Z, so it makes sense that the identity on Z should show up like this, but it can also be verified algebraically, and I will leave that to you, along with the suggestion to first consider the case that rho is a tensor product of two matrices, and then use linearity to conclude that it must work for all rho. And I'll also say that it does not depend on the fact that PA is positive semi-definite, or that rho is a density matrix. This is an equality that would work for any choice of matrices in place of PA and rho, as long as they have the right dimensions for the expression to make sense. And now let's see how the state of Z is affected by the measurement. And the most natural approach, in my view, is to think about the measurement as a channel. Here's the channel that we associate with our measurement. And we're thinking about this as a channel from the system X to a new system Y, whose classical states correspond to the measurement outcomes. So in this formula, sigma represents a state of the system X alone. If we apply this channel to the system X while the pair XZ is in the state row, then we'll obtain the density matrix that we have right here. Again, take as much time as you need to verify this. And again, my suggestion is to first consider the case that rho is a tensor product of two matrices and then use linearity. Now, we saw this type of state, where the first system is classical and the second system is quantum, as an example in the density matrix lesson. Each A occurs with some probability, and that's the trace of the second tensor factor. So you can think about these second tensor factors as being density matrices multiplied by probabilities. So, to obtain the state of Z conditioned on obtaining a particular measurement outcome A, we simply divide out the probability. Or, in other words, we normalize the second tensor factor by dividing it by its own trace. So, in summary, if we perform a measurement on X while the pair XZ is in the state row, this is what happens. First, each outcome A appears with probability equal to the trace of PA tensored with the identity times rho. And second, conditioned on obtaining a particular measurement outcome A, the state of Z is given by the expression shown on the screen, which is what we get by normalizing the matrix we just saw a moment ago, and that's the same thing as dividing the matrix by the probability for A to appear. I should mention that this only makes sense if the probability is non-zero, because otherwise we're dividing by zero, but that's okay because we don't need to concern ourselves with things that don't happen. In this part of the lesson, we'll discuss a simple but fundamental theorem about measurements known as Naimark's theorem. In short, what it says is that any measurement can be implemented as the figure on the screen suggests. Putting this in words, a given general measurement on a system X can be implemented in the following way. We first introduce an initialized workspace system Y, whose classical states are the possible measurement outcomes, which we're assuming are numbered 0 through m-1. Then a unitary operation U is performed on the pair Yx, and then a standard basis measurement is performed on Y. So everything is basically set in stone here, except for the choice of U. And what the theorem says is that it is in fact possible to choose this unitary operation U so that the probabilities for the different outcomes always agree with the given general measurement. Now let's see how Naimark's theorem is proved. And it isn't difficult. We just need to make a good choice for the unitary operation U and verify that it works. But first we need a basic fact from matrix theory, which is that for any positive semi-definite matrix P, there's always a unique positive semi-definite matrix Q, such that Q squared is equal to P. In general, there could be many matrices that square to give us P, but there's always just one of them that's positive semi-definite. The notation we use to denote this matrix is the square root of P, and that's also how we refer to it in words. If you want to calculate the square root of P for some positive semi-definite matrix P, by the way, you can do that by first calculating a spectral decomposition of P, and then replacing each of the eigenvalues by its square root and leaving the eigenvectors alone. The eigenvalues are all non-negative, so this makes sense, and it's pretty easy to see that the matrix we get is in fact positive semi-definite and squares to P. The fact that it's unique is a different matter. It's not difficult to prove that using some basic facts about matrices, but it's kind of tangential to the lesson, and we'll just take that part as being given. And now that we have that concept in hand, it's pretty easy to specify a unitary operation U that works. Any unitary matrix that matches the pattern that's shown on the screen will in fact work. The first n columns, assuming X has n classical states like before, are obtained by stacking the square roots of the matrices that describe the measurement on top of one another, and the remaining columns can be whatever we want. It doesn't make any difference as long as the entire matrix is unitary. And by the way, if you're noticing a resemblance to the connection between Krauss and Steinspring representations of channels, that's not coincidental. And in fact, what we have here is essentially a special case of that, where our Krauss matrices all happen to be positive semi-definite. So there are two things we need to check. The first is that this choice of U actually works, and the second is that it's possible to choose the unspecified columns in a way that makes U unitary. So let's start with the first one. Here's the state that we start with. The bottom system Y is initialized to the 0 state, while the top system starts in the state rho. And then we perform U, which means that we conjugate by U. We can write this all out in terms of block matrices as is shown on the screen. We have U on the left, U dagger on the right, and ket 0, bra 0 tensored with rho in the middle, which takes the form that we have here, where we have rho in the upper left-hand corner and zeros everywhere else. And if you think about this product for a moment, it's evident that the unspecified entries of U don't matter at all, because they're always getting multiplied by 0 entries of this matrix in the middle. And if we work through the multiplication, what we get is this matrix that's shown right here, described as a block matrix, or alternatively, we can express it using Dirac notation like this. That is in fact the more convenient form for us, so let's focus in on this expression. And for the sake of convenience, let's give this matrix, which is a density matrix, the name sigma. The last step is the standard basis measurement on Y. So let's calculate the reduced state on Y, and that's easy given the expression we have. We simply trace out X, which corresponds to the second tensor factor. So the probability for any given outcome A to appear is the diagonal entry corresponding to A. We can write that like this, and it equals the trace of the square root of PA times rho times the square root of PA, and by the cyclic property of the trace, we get the trace of PA times rho, which is what we were hoping for. So the probabilities for the different outcomes to appear are correct. They always agree with the original measurement that we started with. The second thing we need to check is that it's possible to fill in the unspecified columns of U in such a way that it becomes unitary. This follows from the fact that the first n columns, which are the ones that are formed by the square roots of the matrices that describe the measurement, are orthonormal, and that can be checked pretty directly. The relevant details are here on the screen, so pause the video and take a few moments to think about that if you wish. But as I suggested before, it's actually a special case of something that we encountered in the previous lesson. And that is the proof. So far in the lesson, we've kept our focus on destructive measurements, meaning that there's no specification of the post-measurement quantum state of the system that was measured. For a non-destructive measurement, on the other hand, there's not only a classical measurement outcome, but also a post-measurement quantum state of the system that was measured. And as we'll see, there's a natural connection to Naimark's theorem. There are in fact different ways to formulate non-destructive measurements in mathematical terms, but we'll start with one formulation that basically comes directly from Naimark's theorem. Consider a general measurement, meaning a destructive one, described by a collection of positive semi-definite matrices, P0 through Pm-1, that sum to the identity. We can then turn this measurement into a non-destructive measurement simply by considering the implementation of this measurement that we discussed in the context of Naimark's theorem. We introduce a new system Y, interact it with X through a unitary operation U, and then perform a standard basis measurement on Y. So the system X is still there, and we can consider its state. And based on the analysis that we went through, we can determine that the post-measurement state of X, conditioned on getting a particular measurement outcome A, is given by a density matrix that looks like this. In words, we conjugate by the square root of the corresponding measurement matrix, and then normalize. Another way to formulate non-destructive measurements, which is more general, is in terms of Krauss matrices of channels. And this is the definition of measurements you'll find in the well-known textbook of Nielsen and Chuang, for instance. Suppose that m0 through m-1 are square matrices that satisfy the equation that's shown on the screen, which is to say that we could think about these matrices as being Krauss matrices that describe a channel. In fact, these matrices do describe a channel, but they also describe a non-destructive measurement, and the way that it works when a system in a given state rho is measured is, first, the outcome probabilities are given by the equation shown on the screen. Each outcome appears with probability equal to the trace of ma times rho times ma dagger. And conditioned on the outcome A appearing, the state of the measured system looks like this. Non-destructive measurements of this sort can be implemented in a similar way to what we had for Naimark's theorem, and I'll leave that for you to think about if you choose. It is possible to generalize the concept of a non-destructive measurement even further than this. For example, there's a concept of a so-called quantum instrument that's sometimes quite useful, but I won't cover that in this video. In the last part of the lesson, I'll briefly discuss two tasks that are associated with measurements: quantum state discrimination and quantum state tomography. There's quite a lot to be said about both of these concepts, and we're really just going to be scratching the surface. So let's start by clarifying what these terms refer to and how they differ. First is quantum state discrimination. The idea here is that we have a known collection of quantum states of some system, along with probabilities associated with these states. So, to be precise, let's assume that rho 0 through rho m-1 are density matrices representing possible quantum states of a system X, and p0 through pm-1 are probabilities associated with these states. So, if we collect the probabilities into a single vector, we get a probability vector. A succinct way of saying this, by the way, is that we have an ensemble of quantum states. And now, an abstract way that we can think about quantum state discrimination as a task or as a problem is that, first, a number between 0 and m-1 is chosen randomly according to the probabilities. The system X is then prepared in the state corresponding to the randomly selected number. And the goal is to determine, by means of a measurement of X, which number was chosen. So, we have a finite number of alternatives, along with a prior, and the goal is to determine which alternative actually happened. For some choices of states and probabilities, this may be easy, and for others, it may not be possible to do this without some chance of making an error. And there are various specific questions that we could ask, such as, what is the minimum probability of making an error, and what does a measurement that achieves this minimum probability of error look like? Quantum state tomography, on the other hand, is different. Here, we have an unknown quantum state of a system, so there's typically no prior or any information about possible alternatives. This time, however, it's not a single copy of the state that's made available, but rather many independent copies are made available, which is to say that for some possibly large number n, we have n identical systems, x1 through xn, that are each independently prepared in the state rho. And this time, the goal is to find an approximation of this unknown quantum state as a density matrix by measuring the systems. So, in summary, in quantum state discrimination, we have a single copy of the state, and we're trying to discriminate among a finite number of known alternatives. And in quantum state tomography, we have many independent copies of an unknown quantum state, and the goal is to find a description of that state, or at least a decent approximation of it. Quantum state discrimination is interesting because it abstracts a type of situation that commonly arises, in computation and cryptography, for instance, where one alternative out of a finite set of possibilities has taken place, and we, or somebody else, is trying to figure out which one it was by measuring a quantum system. The simplest non-trivial case is where there are just two alternatives, meaning that m is equal to 2. So the task is to discriminate between a pair of states. This case turns out to be essentially a completely solved problem, assuming that the goal is to minimize the chance of an incorrect discrimination. There's an optimal choice for a measurement, and it's often called the Hellstrom measurement. It's a projective measurement, in fact, and it can be described as follows. First, we consider the weighted difference between the two alternatives, meaning p0 times rho 0 minus p1 times rho 1. So we're multiplying the probability of drawing each of these two states to the states themselves, and we're taking the difference. That's a Hermitian matrix because it equals its own conjugate transpose, so it has a spectral decomposition, and we know in particular that the eigenvalues are all real numbers. So let's assume that we have a spectral decomposition written in the form that's shown on the screen. What we do next is to collect the eigenvalues into two sets, where all of the positive eigenvalues are in one set and all of the negative eigenvalues are in the other. To be precise, let's take S0 to be the set of all of the indices k for which the corresponding eigenvalue lambda k is non-negative, and let S1 be the remaining indices, which are the ones corresponding to negative eigenvalues. It doesn't actually matter which set contains the indices corresponding to any zero eigenvalues. Here we're making an arbitrary choice to include them in S0, but it wouldn't make any difference if some or all of them were included in S1 instead. All that really matters is that we're separating the positive and negative eigenvalues. And finally, we define two projections, pi0 and pi1, as is shown on the screen. In words, pi0 is the projection onto the subspace spanned by the eigenvectors corresponding to non-negative eigenvalues, and pi1 is the projection onto the space spanned by the eigenvectors corresponding to negative eigenvalues. These are indeed projections, and if we add them together, we get the identity matrix, because the eigenvectors psi0 through psi n-1 form an orthonormal basis. If this measurement is performed in the situation at hand, meaning that the state being measured is rho 0 with probability p0 and rho 1 with probability p1, then it turns out that the probability of a correct identification has a pretty simple formula in terms of the eigenvalues lambda 0 through lambda n-1. I won't go through the details of the calculation in this video. You can consult the written content linked in the video description if you're interested, or see if you can convince yourself that this formula is indeed correct. We can also express this probability using a matrix norm commonly called the trace norm. It's a similar notation to the Euclidean norm for vectors, except that we have a subscript of a 1 to indicate that it's the trace norm. The trace norm is very important, and it's very commonly encountered in quantum computing, but I won't say too much more about it in this lesson. One way to define it for Hermitian matrices is that it's the sum of the absolute values of the eigenvalues, and so you can think about this second equality as following directly from that definition. The trace norm can also be defined in other ways that are more general, and we'll encounter the trace norm again in the next lesson. This is, in fact, the best that you can do. This measurement is optimal, assuming your goal is to maximize the chance of a correct guess. That fact is sometimes called the Hellstrom-Holovo theorem, and it's also sometimes just called Hellstrom's theorem. So you can't beat this measurement in terms of correctness probability, and it's nice because there's a simple recipe for the measurement itself and an exact formula for the correctness probability in terms of the trace norm. The trace norm is often used as a way of measuring the observable difference between density matrices for precisely this reason. And when people refer to the trace distance between states, they're typically referring to 1/2 times the trace norm of the difference between the two density matrices, which here corresponds to the case where p0 and p1 are both 1/2, which is a natural case to consider. Quantum state discrimination for two states is optimally solved by the Hellstrom measurement, for which we have a simple recipe and a simple formula for the correctness probability. So what happens when we want to discriminate among 3 or more states? In this case, we don't have a formula in general for an optimal choice of a measurement, or a simple expression for the maximum probability of correctness. It is, however, possible to find a good approximation of an optimal measurement with the help of a computer, and in particular, that can be done using a really fascinating and powerful optimization technique known as semi-definite programming. But it's not something that you can feasibly implement using a pencil and a piece of paper, for instance. On the other hand, if somebody gives you a description of a measurement and they claim to you that this measurement is optimal for a quantum state discrimination task, then it actually is very easy to either verify or falsify that claim. And that can be done using the so-called Holovo-Ewan-Kennedy-Lax conditions. I won't explain what they are in this video, but they are simple conditions, and it's pretty cool that this is possible. Here's an example, which connects back to the tetrahedral states that we saw earlier in the lesson. Suppose we're given one of these four states selected at random, with probability 1/4 for each one. And our goal is to determine which state that we're given. It's not surprising, perhaps, but the best choice you can make for a measurement to do this is the tetrahedral measurement. You can't always do something like this for an arbitrary collection of pure states, but because of the symmetries involved here, this does work and we actually get a valid measurement. And through the Holvo-Ewan-Kennedy-Lax conditions that I mentioned a few moments ago, it turns out to be quite straightforward to prove that this is indeed an optimal choice of a measurement. Specifically, what happens here is that the measurement is always correct with probability 1/2, which isn't bad because there are four alternatives. So the probability of a correct guess is twice as good as random guessing, and it happens to be the best that you can do for these states. Now I'll say just a little bit more about quantum state tomography, where we have many independent copies of an unknown quantum state, and the goal is to find an approximation of the density matrix that describes that state. There are actually several different variants of this problem that depend on your assumptions, and in particular on what sorts of measurements you allow. For instance, we could demand that each system is measured individually, and the results are combined somehow to arrive at a description of the density matrix. Or we could allow all of the systems to be measured together as a single compound system, which is much better in theory, but it's also much more demanding from a technological standpoint. In addition to the choices one makes for the measurements, there's also an important consideration, which is how to reconstruct a description of the density matrix from whatever data you get from the measurements. I won't go into details about this. My point is simply to suggest that quantum state tomography is really more of an umbrella concept having many different variants, as opposed to being a single procedure. There's been a great deal of research into this problem, including some fairly recent breakthrough results that connect the number of copies n to the accuracy of the approximation that can be obtained. And it continues to be an interesting and active area of research. To finish off the lesson, let's take a look at quantum state tomography for qubits and how we can do it. So let's suppose that ρ is a density matrix representing a state of a single qubit, and x1 through xn are qubits that have all been independently prepared in the state ρ. And for the sake of this discussion, let's assume that n is large. What we can do is to divide the systems into three roughly equal piles, and for the first pile, we'll perform a measurement with respect to the plus-minus basis. For each outcome corresponding to plus, we'll score +1, and for each outcome corresponding to minus, we'll score -1. A more succinct way to describe this measurement is that it's a poly-X measurement, because the plus and minus states are eigenvectors of the poly-X matrix, and the corresponding eigenvalues are +1 and -1. And in fact, that's also a much more common way to describe it. And indeed, the expected value for the score is equal to the trace of sigma x times ρ. Now, we don't necessarily learn what this expected value is, but if we average the scores we obtain over lots and lots of trials, we're pretty likely to get a decent approximation to this expected value by the law of large numbers. And there are some well-known statistical bounds that we can throw at this if we want to be more quantitative about that statement. We do something similar with sigma y on the second third of the systems. The only thing that changes here is that we use the plus I and minus I states, which are eigenvectors of sigma y. And similarly for sigma z, for which the standard basis vectors are eigenvectors. And then finally, we can use the formula that's shown on the screen, which tells us what the coefficients should be if ρ is written as a linear combination of Pauli matrices. And by substituting our approximations for these coefficients, and possibly adjusting them a little bit to make sure that we get a positive semi-definite matrix, we get an approximation to ρ. Of course, there are details that I haven't gone into, such as the accuracy of the approximation and the degree of confidence that we can hope to have in it, but hopefully that gives you a basic idea of one way that tomography can be performed on a qubit. It's also possible to do qubit tomography using the tetrahedral measurement, and in fact this turns out to be quite simple and elegant, at least in mathematical terms. What we can do is to perform just this one measurement alone on all of the independent copies of our unknown quantum state, and by using the remarkable formula shown right here, we can come up with an approximation of our state by estimating the trace of pk times rho for each k by the fraction of times the corresponding measurement outcome appears. Again, this only works because of the perfect symmetries that we have among these four states, and there are in fact some really fascinating unsolved problems that relate to generalizations of this approach to larger systems. And that's a good place to stop the lesson. Thank you for watching, and I hope that you will join me for the next lesson, which is about purifications and fidelity. Goodbye for now.